Greetings everyone, my name is Nafis Faisal and I am making this demo video as a part of my application to BRAC University for the post of Triple E lecturer in the Department of CSE. I will be presenting my video on digital image processing. Now, let me begin by stating what image processing is. So, image processing is any of the processes that involve the image that an image goes through to provide one of these three things. It can enhance the information in the image. It can also extract some information from the image, or it can process it for making it better suited for compression or transmission or any such process. Now, we will later see that if an image is if an image is taken as is without any compression, it gets pretty large pretty quickly. So compression techniques are very much useful for storing images in a practical way. uh, uh, at this on at Right now, I'd like to state the difference between imaging and image processing. This is something that we need to be clear about. Now, I've already stated what image processing is. Now I'll state what imaging is. So image processing, I've already stated. So imaging is the process of actually taking the image, process of capturing an image. So that's what imaging is. So we will not be concerned much about the process of imaging. I will shortly describe it, but we will mostly be focused on image processing techniques. Now, uh, I'll define what an image is and what a digital image is. An image is a function, right, of two spatial variables. So it's spread in two directions. Uh, we can we actually know this from our intuition whenever we see an image that it is just a 2D grid of colors. So it's a function of uh, two spatial variables x and y. But what's a digital image? Well, when I say that an image is a function of two spatial variables, I do not mean that they are discrete in any sense. We actually consider them to be continuous. Both f, the output f, and the spatial variables. But whenever we talk about digital images, as we know that computers actually have finite storage capabilities, and also any kind of processing done in computers have to done using finite blocks of memory and finite actions. So it cannot accommodate anything that is continuous or has an infinite range of values. So digital images are images where the f, that is the output, and also the spatial variables all are discrete and bounded. So digital images are images where spatial variable x, y, and the output f are all finite and discrete. So suppose we have an image. So I'll also talk about the representation of images here. Images are actually represented in this way, where the x spatial axis goes actually from top to down, and the y-axis goes from left to right. It's different from what we usually use, but we must also mention that this is still a right-handed frame of reference, a right-handed coordinate system. Now, this is the origin, and any point here corresponding to any point is an intensity value. What we mean by this intensity value will be cleared up in a bit, but what I want to say is that at every point of this is an intensity value. Let me be precise. It's actually, it can be white or it can be black or it can be anything in between. For now, in colorful images, there are actually three layers of these values: red, green, and blue, each giving a different shade of red, green, and blue, and they combine to form the colors. Right now, we are concerned with a single channel that is only black and white images, or even grayscale images to be precise. Now, what I was saying is this is actually an image, a continuous image, because I haven't actually marked the grid or anything. So if we discretize the spatial axis and quantize the values of the function of the intensities, then what we get will be a digital image. So if we just sample along the x and y axis, then what we get is a digital image. Not only sample, but also uh, quantize each and every one of the values, as we have learned from our signal processing course, what quantization and sampling means. So there, our signals were one dimensional. Here, it's two dimensional. That's the only difference. And well, this can actually be represented as a matrix because this one here is F00. This one is F01. This one is F10, where I am writing like this. So this image, let me call it capital F, can be represented like this. And if there are m rows and n columns, this is an m cross n size matrix or an m cross n size image. So that's image representation. I think my time is up, so I'll end this here. I could have used slides, but I don't think that would actually show how I could do without them. So I can make slides, but I haven't gone for that approach here. So thanks for listening to me. I'll be ending the lecture here.